All right, part two, wind instruments. So, wind instruments produce sound from the vibrations of standing waves in columns of air inside a pipe or a tube. Now, in a string, the ends are notes, but in air columns, the ends can be either notes or antinotes. So, what you need to understand is we're going to deal with those wind instruments that are open on both ends, and we're going to deal with wind instruments that are closed on one end. All right, remember this is like our saxophone, or if you blew across a bottle, whereas these would be things like our clarinets open on both ends. All right, so you handle them differently. An open tube is handled identical to a string. Okay, so the fundamental frequency is the first harmonic, the second harmonic is the first overtone, the third harmonic is the second overtone. So the overtones are one less than the harmonic, and this works exactly like it did in a string. Now, the formula is also exactly the same for an open tube as it was when we did the string. So it'll be NV over 2L. This is again for open tubes. Now for half closed tubes like bottles, saxophones, things like that, or sometimes instead of saying half closed, it'll just say closed because it's closed on one end. They are set up differently because they have to bounce back. And because they have to bounce back, the wavelength is actually only a fourth of a wavelength instead of half of a wavelength. So what happens is we have a first harmonic, and then we skip the second harmonic and go straight to the third harmonic, and then we skip the fourth harmonic and go straight to the fifth harmonic. So these harmonics only work in odds. Now the overtones are still first overtone, second overtone. So it doesn't match by saying that it's going to be one less when we're dealing with half closed tubes. Also, the formula changes to NV over 4L. Again, since the wave has to bounce back, it takes 4 times the length to actually create an entire wavelength. So it's just something to realize that if you have a closed tube, you use 4L instead of 2L. We will be doing a lab on Tuesday in between our test days on Monday and Wednesday, and it will be dealing with closed tubes. It's really a cool lab. It'll be fun. Okay. When we're talking about harmonics, again, it's really, really, really important that you have this in your notes. For open pipe, the harmonics are all the multiples. They're the first harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic. Now the overtones match it exactly. There's not one with the first, but it's the first overtone, the second overtone, the third overtone. So the overtones are just one less than the harmonic value. Okay? But for a closed pipe, the harmonics only go by odd multiples. So the harmonics go first, third, fifth, and seventh. Now the overtones are still ordered up the same way in that there is no overtone with the first or fundamental harmonic. But then this will be the first overtone, this will be the second overtone, this will be the third overtone. So the overtones only go with odd multiples of the harmonics for a closed pipe. Really, really, really important to have in your notes. I have some examples here since it's open on both ends. I have 1.32 meters long. Okay, I'm going to go ahead and say that since it's a pipe and we're dealing with a wind instrument, the velocity is 340 meters per second. That's the value that you'll use in your calculations if you aren't told what it is in air. Our length is 1.32 meters. And so since it's open, we'll use F equals NV over 2L. We are looking for the fundamental frequency. Since it didn't specify, we're just going to look for the first frequency. And so we'll use a 1 there, and we'll get 128.79 hertz. Hopefully you guys are awake still. All right. So what if it was closed at one end instead? How would that change this formula? Think back, think back. If it's closed, then you should have a 4 there instead of a 2. So it's NV over 4L. So when you plug in your numbers, you should end up with an answer that is 64.39 hertz instead. So this will create a different pitched sound, because remember pitch and frequency are tied together, than this will create. So the bottle will create a different frequency than the pipe that's open on both ends. All right. I have a pipe organ again that's open on both ends. Fundamental frequency I'm given, and I'm looking for the length of the pipe instead. So I have my fundamental frequency. I have the speed of sound and air given to me in the problem. Since it's open at both ends, I'll use NV over 2L. Since it's the fundamental, N will be 1. I'm looking for the L, so I'll switch where the 370 and the L are, and I'll end up finding out that it is 0.45 meters. So just different ways to rearrange that equation. Now this one example, it's a saxophone. If you remember back at the very beginning when we talked about the types of instruments, a saxophone's a closed pipe. So with this formula, this one we'll have to use F equals NV over 4L. I'm given all the information. Third harmonic would mean that my N is 3. I have my frequency. I have my V. I would be looking for my L. And again, it would be my F equals NV over 4L. Not going to take the time to work all of this out though. All right. Then if I have it again, if it says it's closed on one end, if it's the seventh harmonic, my N value would be 7. Frequency was given to me. The pipe length was given to me. I would now be finding the V, or the speed of the sound in this pipe. Okay. Since it's closed on one end, I'd use F equals NV over 4L and then solve for V. All right, I'm going to stop there before this last portion. Again, hopefully all is going well, and you'll just need to listen to one other recording.